Okay, so example 2 here in the optimization here, 4.4. It says if 2,700 centimeters squared of material is available to make a box with a square base and an open top, find the largest possible volume of the box. So this is an optimization question that you'll get. You're given a certain amount of material. You want to optimize the volume of the box. You want to make it the maximum volume you can given that much material. So first, remember the first step there, and I'll just go back to, let's see, this document right here. It says set up a relation involving the quantity you wish to optimize. Okay? And so and you can use the other quantities that are given in the question. So what do we want to optimize? Volume is what we want to optimize. And the volume of a box is given by, well, it's a square base box, first of all. So we've got, let's make the bottom of the box x. So the base dimensions are x by x. Okay? And we'll make the height of the box, we'll make that y. Okay? So here's my nice little box there. So we're going to go x squared y. All right? So again, two variables are good, but we can't do any calculus on two variables right now. We need to write it in terms of one. Well, I mean, it's not possible, but for the sake of ease here, we want to make sure it's in terms of one variable. So we need to look at this other information. So the material is available, and it's a square base with an open top. So this amount of material is made up of what? Well, we've got a square base here. That's x by x. And we've got basically four sides, right? So it'll kind of look like this, and look like this. And these are, y is this dimension right here. Okay? So that is the surface area, okay, of this box is x squared plus 1, 2, 3, 4 xy. Very good. Okay? All right. Now the surface area is given to us as 2,700. Whoa, what happened there? 2,700. So here's our equation relating the two variables. Now, can we write this in terms of just one variable? So can we isolate one of these variables? It looks like that we can isolate for y here. So this looks like this. 2,700 minus x squared divided by what? Divided by 4x equals y. Okay, does everybody agree with that? And so here is what y equals. So now I'm going to put this into my relation here and make it a function in terms of only x. So volume is now going to be a function of x. It's going to be x squared times, and what is y? 2,700 minus x squared over 4x. Okay, so that step right there is very important. You guys getting that step? Do you understand what we're doing here? Making a function, using this extra information right here to do that. So you might want to just simplify this expression here now a little bit. So the 1x is going to go with this x, which is going to multiply in. So it's going to be 2,700x minus x cubed. And that's going to be all over 4. Okay. Okay. So now the volume, if we take the derivative of the volume here now, and you could treat this as a quotient rule if you want. You could write this as two separate fractions if you want. Doesn't matter. You could pull a 1/4 out if you want. It doesn't really matter. Yeah, it doesn't really matter what you do. We could do. We could pull that 1/4 out. I would say, pull the 1/4 out. It's just a constant. So we're left with and I guess this is still the volume. I'm just rearranging this some more. This is now 2700x minus x cubed. Right? Understand that? Is that good? So the derivative now, that 1/4 can just hang out there. It's constant, so it just stays there. And then the derivative of this would be 2700 minus 3x squared. Now, you can just leave it like that if you want for now, because we've taken the derivative, and what we want to do now is what? What's the next step? Okay, relation function, find the derivative, identify critical numbers right here. Understand that a local max or min, that's what we're trying to do. We're trying to find an optimal solution here. It's going to happen at a critical number. So the question actually asked us to do what? Find the largest possible volume. So we're going to maximize the volume. We want to find x, basically. That's what we're trying to do. Find the x that gives us a maximum. So we'll let this equal 0. 0 equals. And of course that 1/4 now just kind of goes away. You multiply both sides by 1/4 or by 4, and 4 times 0 is just 4, and that 1/4 is gone. So we have 3x squared equals 2700. X squared equals 900. And x equals, now technically plus or minus 30 here when we take the square root of 900, right? Technically. But remember, we're looking for a length. So a negative length does not make any sense. So you would reject the negative value and you just keep the positive, right? So just remember when you're doing this, take the square root. In terms of the question, we're looking for a positive. So it looks like the length x is going to be, this function is going to be optimized at 30. Now, does it make sense that this will give us a largest possible volume? Well, okay, what you could do is you could do some trial and error, I guess, right? And you could plug this number in to see if other numbers other than 30 give us anything bigger for a volume. But let's find out what y is first so we can just take a better look at this. So here's x. Let's plug x in here and over here to find y. So 2700 minus 900 would be, is that 1800? This is 120. 180 divided by 12. What's that going to be? 96. What's that? It says, what's 180 divided by 12? 15, right. 1.5. Okay, 15. So if we've got x is 30 and y is 15, that's what they're saying will be the values that will give us a maximum volume. So I don't know if you guys noticed in the first example we did that the optimization kind of came where the dimensions were sort of similar to each other. If you have a really skinny box, but it's super skinny this way, actually this has got to be a square bottom, I guess. So if you have a small square bottom, but the box is really, really tall, right? Do you think that that's going to give you more volume than a bigger base with a shorter height? Okay. So if you want to test, again, what I would suggest you do is find the volume here, which we will, but test other numbers just to see if it's going to be greater than or less than. Okay. But I guess the one thing is when you only have one critical number that you find that's applicable to the question, okay, then that's going to be the one you're looking for. But we'll check anyways. So what's the volume now? The volume is, we said x squared times y, or this volume here when x is 30 is 30 squared times 15, right? So that's 900 times 15. is 1350. Okay. So if we had a different number other than 30, so let's take a number that's just either just more than 30 or just less than 30, and we can give it a try. Right? So what number would be, what number do you want to try? You want to try 40? Maybe? What if this box, well actually let's try a smaller box like I suggested here. So let's do x is 10. Okay, so 10 by 10. All right, that's going to be kind of something like this box here, but then this is going to be quite a bit taller, isn't it? So let's try it. So if x was 10, let's test. X equals 10. Then if x is 10, what is y? Well, we have to recalculate that too, don't we? So 2700 minus 10 squared is 100. So that's 2600 divided by 40. Sound right? What's 2600 divided by 40? Is 65. So we are going to have a height of 65. What's the volume with that when x is 10? Well, that's going to be 10 squared times 65. That's going to be 6,500. All right? Now look at this. We've got a volume here of 1,350, whatever the units are, right? Centimeters cubed. So look at how big this one is compared to this. Wait. 65. What's that? I forgot a zero. Thank you. 13,500. Yeah. Is that right? Yep. Sorry. You're right. Thanks. Thanks for letting me know that now. I'm like, what? Why? Wait a minute. Wait. 1,300? No, 13,000. Oh, thanks a lot. That's great. So this is smaller than that one. So the volume is not going to be like another number here. You could try 40 or 50 if you wanted to, and you're going to find that this is going to be the largest number that you're going to get with any dimension of the box that you're going to get. Okay. If you wanted to graph, you could also graph your volume function. You could graph the original function, and you would see that you would have something like this, like that, and then the maximum point should be right around 30 here. So this would be your volume function right here. Now the thing is, though, when you're being tested on this is not a graphing calculator sort of section here. So I don't want you just to stop here, graph it, and find the maximum point and be done. You do need to go through the calculus method, right? So, but now, while you're doing this, I mean, you can check on your graphing calculator to see. And that's what I would probably suggest. Instead of testing numbers, like this, you could just check with a graph if you wanted. Okay?